name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. Welcome to my Not a Lecture video series. These videos are really meant to not be lectures, but instead to be examples of problems that you would see within homework. As always, it is assumed that you're watching the lectures that your professor is providing, as these videos are no substitute for an actual lecture. So what is this video about? Well, you're likely running into this because it's embedded in a homework problem in an online homework system, or maybe you're surfing YouTube and you found it for some odd reason. In this video, we're going to talk about finding the domains of products and quotients of functions. You likely have a very specific example that you'd like worked out. However, I'm not going to do it. Instead, I'm going to show you how to do things in general. Well, what do I mean by finding domains of products and quotients of functions? Well, I mean that you have a couple functions. In the first case, we have something like a logarithmic function times a radical function, or you might have a quotient of functions. So we might have a radical function being divided by a polynomial. In any case, finding the domain of a product or a quotient is relatively the same. You just want to know where each function that you're looking at is undefined, or better yet, it might be a better way of saying it if you said, what x values can we plug into this function? That is, this specific function, the log of 9 minus x, what is its domain? And then the square root of x plus 4, what is its domain? And then looking at the next example, asking yourself the square root of x, hey, what's that domain of that function? And then again, this denominator, what's the domain of that function? Now, just to let you know, when you're dealing with quotients of functions, like you see right here, there's an added extra little bit of care we need to exercise when finding the domain. So let's go ahead and tackle just both of these examples to showcase how this is done. And I promise you, this extends to any example that you're working with, as long as it is a product or a quotient of functions. So let's take a look at this product of functions first. The first thing you're going to want to do is look at each of those sub-functions and determine what is the domain of that sub-function. For example, the log of 9 minus x. Now I'm assuming that you already have gone through logarithms. If you have not, then you can ignore this conversation. However, it still applies to the vast majority of students who are going to be watching this video. You should know that logarithms can only take positive numbers as their arguments. That is, that argument right there has to be positive. So I'm going to initially state that 9 minus x, the argument of the log, must be greater than 0. Adding x to both sides, we get the domain of this function. All x values are allowable as long as they are less than 9. Now we move to the second function in that product, and that is the square root of x plus 4. The square root function has a domain restriction as well. The argument of a square root function, that guy right there, has to be greater than or equal to 0. So let's go ahead and write that down. Now that we have that inequality written down, we happen to be able to solve that. Just subtract 4 from both sides, and we get the restriction that x must be greater than or equal to -4. Now with products and quotients of functions, which is what we see in the white ink over to the left-hand side there, f of x, each time that you find the domain of a function within that product, it further restricts the overall domain of the product. That is, if I look at a number line, and I start with the assumption that I can plug anything from this number line into the values of x for that function f of x, well, as I start to find the relative domains of both the log and the square root function, it starts to restrict what our x values can be. So in blue ink there, I find out that I'm restricting my domain to all x values less than 9. However, I have a further restriction in green ink there that all x values simultaneously have to be greater than or equal to a -4. And therefore the domain of f of x, which is the log of 9 minus x times the square root of x plus 4, is the intersection of those domains, basically all the restrictions put together. So I'll go ahead and just draw out that domain here by shading this number line all the way over to the right. And you should be familiar at this point with interval notation. If you need a review of that, that's a different video. And so when I answer the question, what is the domain of f of x, which is that white function right there, it is going to be -4 to 9, including -4, but not including 9. And you know, the notation I'm going to use is d sub f, which means to me the domain of the function f. Now, if you happen to be in calculus, I would recommend that you ignore my notation right there because that is the differential operator notation for derivatives. But don't worry about it. You can ignore that sentence otherwise. Really, this is just a nice way of saying the domain of the function f is -4 to 9, including -4, not including 9. Now, what about quotients? Again, this may not be your exact problem. It doesn't matter. I'm teaching you how to find the domain of any rational function, or any ratio of functions, I should say. So again, you start by considering each function separately. For example, the numerator, square root of x. I happen to know that the argument for the square root must be greater than or equal to 0. So I'll start with that. That x simply just has to be greater than or equal to 0. Very, very nice domain restriction. Now let's go ahead and take a look at the denominator. Well, the denominator is very nice because the domain of that function, x squared plus 5x plus 6, is all real numbers normally. So I'm going to go ahead and write that over to the right-hand side. But here's where ratios of functions differ from products of functions. Because that second function, x squared plus 5x plus 6, is in the denominator of this function g of x, we have to have that further restriction that, by the way, that polynomial cannot ever be 0. Otherwise, we will be dividing by 0. So I'll write that over here. Well, using a little bit of our prerequisite factoring, we find that the product of x plus 2 and x plus 3 cannot be 0. That is, x cannot be a -2 and it cannot be a -3. Well, actually, we don't need to really worry about those restrictions in this kind of fictitious case because we have this further restriction that x has to be greater than or equal to 0. So it's never going to be -2 or -3. However, it still is important to kind of note that right here. So the overall domain, if I were to draw out a number line, and this is why we teach you to draw number lines way back when, is because when you're working with domains of functions, it tends to make the work a lot easier. So I'll start by saying, well, this function right here requires my x values to be greater than or equal to 0. So I need all of these x values to the right. And the second function, or the denominator, well, it normally has a domain of all real numbers. However, we cannot include -2, nor can we include -3. But if you look at our number line and where we're highlighting, -2 and -3 are not even there anyway. So we can kind of ignore that specific restriction. And so having highlighted that, we can easily see the domain of g of x is going to be all real numbers starting at 0 and climbing up to positive infinity. And there we go. I've actually written that same notation that I was writing before. Now, to be honest with you, I didn't like that last example. I just kind of made it up on the fly. So let's go ahead and do one last example of a ratio of functions, because products are pretty easy, but ratios tend to need a couple examples. And if you've been watching my example series, you know that every once in a while, near to the end, I sneak in kind of the example you're working on or something like it. So that's what I'm doing here. This could be embedded in a problem that's very similar to what you see right now as h of x. So let's take a look at both of those functions, the numerator function and the denominator function. So the numerator function is a square root of 11 plus x. And we happen to know, again, that even indexed radical functions need non-negative arguments. That is, the argument 11 plus x has to be greater than or possibly equal to 0. That's perfectly fine if it's equal to 0. So subtracting 11 from both sides, we get that x is greater than or equal to negative 11. And by the way, I put some implication signs in there, basically saying the square root of 11 plus x implies that 11 plus x must be non-negative, which implies x has to be greater than or equal to negative 11. Anyhow, the denominator, on the other hand, 5 minus x, well, the domain of that is all real numbers. I'm not even going to bother writing that down because there's really no need. However, I am going to write down the fact that 5 minus x cannot be 0. Adding x to both sides of that inequality, we get that x cannot be 5. Now, drawing a number line for this quotient of functions, the first condition tells us that I'm going to consider all x values greater than or equal to a negative 11. So I start highlighting to the right of negative 11. Of course, the bracket means I'm including that negative 11. And then I see that the green ink tells me I cannot possibly include x equals 5. So as I highlight to the right here, I'm going to skip over x equals 5. Otherwise, I can continue highlighting every other number on this number line. I just can't have 5. And that gives me a visual of the domain of h of x. And therefore, the domain is negative 11 to 5, including negative 11, not including 5, union the interval from 5 to infinity. Again, not including 5, and you never include infinity or negative infinity. When I read this out loud in a class, I say, we have an interval starting at negative 11, going to 5, skipping over 5, and continuing on to infinity. That's a great way to read that. All right, that's the end of this Not a Lecture video. I hope it helps you. Have a great day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.